is Professor Warner, Tom Warner, as we call him. And his research interests are numerical weather prediction, regional climate modeling, mesoscale dynamics, and arid land meteorology. During the 80s, he led in Penn State University a research group that developed the first operational numerical weather prediction model that was capable of representing mesoscale weather processes. I am familiar with that close end from the first period. I will describe it later in my talk. That effort contributed to the proliferation of dozens of similar modeling systems worldwide and are used for public weather forecasting. Now it's not dozens, it's not even hundreds now. I think it's thousands of locations. Is it correct? Since taking the position at NCAR, which is the National Center of Atmospheric Research in Colorado, he has been the lead scientist for a number of projects and has involved in the development of improved operational weather forecasting system. He authored a book on desert meteorology. You know, when you sent me this book, I was surprised. Penn State University, when I came, my big surprise was it's raining all the year, about the same thing every month. And it's green all the year. And then Tom is writing a book on desert meteorology. I couldn't believe it. It was published in Cambridge University Press, and now a second book is coming on numerical weather and climate prediction, also in Cambridge University Press. And this is certainly of interest for us in this semi-arid zone. And I'm looking forward to listen to you. I know it's not the same talk. Please. Thank you. Please come here. I think your talk is here. Tom Warner. Here it should be.
I want to thank you for the opportunity to be here. It's really a pleasure, and it's been a very enjoyable visit. This is a list of the things that we're going to talk about this morning. A few different ways of getting higher resolution in models, and a lot of them I think we don't think about very often. So we're going to touch on that. We're also going to describe the rapid growth and specialized applications of high-resolution numerical weather prediction. Talk about the trend toward even higher resolution, and that sometimes involves these large eddy simulation models. Coupled higher resolution meteorological models with specialized application models. Thank you. There will be another topic. Spend a little bit of time talking about better verification metrics for high resolution models that are fine. Conventional metrics are fine for coarse models, but high-resolution models need some special efforts. And then also finish up with a discussion about quality assurance in numerical weather prediction. Now, a few approaches for achieving higher resolution. What you see up here is the traditional approach of nesting a limited area model within a global model. So this is Louis' global model up here. And we would just take a weather research and forecasting type model with a nested configuration like this, zoom into an area like this, which happens to be an Army test range for which we've developed a forecasting system, and this would be very high resolution with computation points a kilometer apart. But sometimes we don't think about vertical nesting. With traditional models, this is what the cross-section of the grid, that doesn't mean north, you look at it from the side, and that's the Z coordinate there. So in any case, here's your fine resolution grid in the middle of the coarse resolution grid there, and your only option is to have the high resolution all the way up through the atmosphere. And maybe you don't need it up here. Maybe you just want to resolve boundary layer processes down near the ground, but you're wasting all the computational resources up there. So some models, not very many, not enough, allow you to do vertical nesting. So over here, we just have maybe a boundary layer process that we want to resolve. So the high horizontal resolution only goes up this far, and then you switch to coarser resolution. So that's another approach for getting high resolution there. Something that's another approach that's used much less often is to have a global stretch grid. So it's a latitude-longitude model, latitude-longitude coordinate system that allows a variable lat-long, and so we have an area in here where we have a relatively uniform grid. It has, unfortunately, an equally high-resolution zone on the other side of the world that you're wasting your computation time on, but this doesn't have the same boundary condition problems. And this is a uniform high resolution over the whole planet. Now, there aren't many grid points there. There'd be a lot more in a real model, but this is just to illustrate. Now, there are some trade-offs here when we're deciding which approach to use to get higher resolution. Here's the high-resolution global model we saw last. This is the stretch grid model, and here's the nested model. In terms of computational expense, this is expensive here, obviously. This is less expensive. In terms of lateral boundary condition effects, here they're large. There are none. So, which one you want to accept is, a major decision, I think. Another approach is a dynamically adaptive grid. So instead of having the grid points always the same distance apart, we adjust the resolution during the forecast based on the processes that are going on. In this case, we have a hurricane developing off of the southeastern coast of the U.S. Up here, where nothing is going on, we have the computation points far apart. Down here, the model automatically produces a higher resolution grid, and that higher resolution grid follows the hurricane along. This is great, but it's a real mess to code, so you would never let your students work on something like this. So it has a downside as well, but that is another way of getting higher resolution. We'll go through a list of some examples of high-resolution weather prediction. These are specialized applications. It's not a National Weather Service type application of models where we have to serve a large community, so these are specialized. And these are just examples from NCAR because that's the graphics that I have. There are hundreds of organizations worldwide that are doing the same sort of thing in the same way, so I don't want to make it sound like anything special is going on at NCAR in that sense. One of our first projects was to provide operational weather support for Army test ranges throughout the continental U.S., including Alaska. So for each one of these black dots here, there's an Army test range. They need operational weather prediction at very high resolution. They are located along complicated coastlines like you are, a lot of mountains and local meteorology that requires horizontal resolution that's, on the order of 1 kilometer, perhaps. This, by the way, is one of the reasons why I got interested in desert meteorology, in addition to talking with Pinhas for the last 20 years. 4 of the Army test ranges are in desert climates. So another application is for the Athens Olympics. This is for general weather support, but also in the event of a terrorist release of a chemical, dangerous chemical in the area, we need to calculate which direction it's going to flow in. So the blue arrows here are an example of a forecast from the MM5 model, and the red lines are the observations. And the little green circle at the end of the red line is the head of the arrow. You can't see it very well, but in virtually all instances in this complicated wind field, the model replicates the observed wind field. There's one place in here where it's 180 degrees wrong, but thankfully you can't see the green dot very well, so you wouldn't know it if I didn't tell you. Anyhow, so we supported the Olympics there. For Operation Iraqi Freedom, shortly after 9/11, we applied the MM5 model to support the military there, and this is an especially high-resolution grid where we actually resolved the impact of Baghdad, red there, on the local meteorology. So different surface conditions there. We have a lot of wildfires in arid climates, at least in the U.S., and they need special weather support. Often the fires are in complex terrain. Weather service models are not high enough resolution to represent the details of the wind flow pattern, so they need these forecasts to keep the firefighters safe, those on the ground and in the air as well. So we provided operational support for a few different wildfires in Colorado and Arizona in the western U.S. Again, with the theme of the Olympics, this is the Torino Olympics and one of the model grids there. Salt Lake City Olympics, again, there was concern about the terrorist release of hazardous material. So this is the Great Salt Lake here, and the color shading shows mountains in here. And in this example, we had a release of hazardous material up here, and the red line shows the dosage moving down the valley, and the green shows the concentration of the material as it's being lofted over the mountains during the daytime diurnal heating cycle. We set the model up for West Africa to predict rainfall in the Sahel for a year for a special application. This is an example of a specialized model for the Washington, D.C. area. This is specialized because it ingests Doppler LiDAR data. And from that, we incorporate other observations and get the full 3D wind field. So in this case here, you see a gust front moving from the northeast across the city, and it's about at the Potomac right there. Relatively weak winds here, but 3 or 4 times faster up there. So you get a map like this with 100-kilometer grid increments about every 6 minutes. So it's a really nice forecasting tool if you can afford the LiDAR. The focus down here at the bottom, there is a National Atmospheric Release Advisory Center at Lawrence Livermore National Laboratory, and they predict the weather when there's an incident of national significance, it's called. For example, if there's a rail car filled with chlorine that overturns and threatens the local population, or if there's an intentional release of toxic material. This NARAC here provides the forecasts of the weather. It's the official forecast in these emergency situations, but they didn't have any urban scale models. So they wanted one for the New York City area for obvious reasons. So we, for 3 years, set this WRF model up to provide operational forecasts over this grid and automatically input them to this advisory center there. As part of our support of the military, there's a missile test center of the Navy on the island of Kauai in the Hawaiian chain, and we provide operational weather support for them when they have special tests. There are commercial applications, high-resolution applications as well. A company called AirDat manufactures meteorological sensors for commuter aircraft. I mean, the meteorological sensors, of course, have been on wide-body aircraft for a long while, but commuter aircraft have a lot of ups and downs all day long, so you get a lot of lower atmospheric soundings if you put sensors on them. And the business model for AirDat was to put the sensors on the commuter aircraft, take the observations, and sell them to the Weather Service. That business model didn't work out, so now what they're doing is paying NCAR to set the model up, use their data, and produce operational forecasts that they can sell, AirDat can sell. And the idea in principle is that because of those special data, the quality of the forecast will be better than what you get from the Weather Service. It remains to be seen, really. We're working with a wind energy company, Xcel Energy. It's the biggest provider of wind energy in the U.S. right now, and we'll see later on that they need good wind forecasts. So let's continue to focus on specialized applications of high-resolution forecasting, but zoom in on the wind energy problem, because that's a big one currently. Many states in the U.S. have a goal of providing 25 to 30% of their energy, electric energy, from wind by the year 2020 or sometimes 2030. A big problem is that wind forecasts are not accurate enough to make that possible right now. So the predictive skill for wind is going to have to increase dramatically over the next 10 years in order for that goal of energy independence, at least to that degree, to happen. And this is an example of one of the problems that energy companies have. This is power produced in one section of the country and in megawatts here, and the colors correspond to different wind farms. And this is time across here, 9 hours from left to right. So as time progresses, we see the amount of energy, look at the top of the envelope here, the amount of energy that's coming from these wind farms varies a lot. Here and again, the colors correspond to the different wind farms. So you get a big spike in the energy here from the yellow one. The rest of them stay about the same. These are convective events here, gust fronts increasing the wind speed and increasing the power. This is a cold front here. But look, you have energy from the wind varying from almost 0 up to 800 megawatts in a matter of hours. This will drive the power companies crazy. They can't use power like this unless they know the wind is going to change. So big problem there, meteorologically, modeling-wise, and otherwise. We call these ramp events, by the way, for obvious reasons. Ramp ups are big problems. Ramps down are too. If it ramps down quickly and they don't know it and they don't have coal plants or gas plants already running, you'll have a power loss for the population. So meteorological causes of ramp events, we can guess at them, of course, pretty well. Gust fronts, low-level jets, wind bursts in the stable boundary layer, synoptic scale cold fronts, and so on. So in principle, we need to be able to predict all of these things reasonably well in order to do a good job for the energy companies. This is a nowcast using the NCAR auto nowcaster of a gust front in Colorado. We see this is from a Doppler radar. We see we have high winds behind this convergence zone here, same thing over there, and this gust front is approaching a wind farm. And they need to know that when it's going to happen. So nowcasters are also important tools here. This is an example. This is by Yubao Liu, one of our guests in the audience. He's one of our chief modelers in my group. And this is for a particular wind farm in Colorado. They have 274 turbines there. Each turbine has a little anemometer on the top of the nacelle. The nacelle is the housing around the generator. Now, it's not a good place to measure winds, obviously, because you have the dynamic effects of the turbine, but it's easy to put one there, and it's still useful information. These curves here, again, this is time, and this is wind speed up here. There are 274 curves here, different colors, and they show the evolution of the wind on each one of these turbines as a function of time. This is obviously a ramp event of the sort that we were just talking about with a lot of other spikes in there. But another important thing to see is the range of wind speed just across this relatively small wind farm. It's only 10 or 15 kilometers, but you get a 10 to 15 knot variation in the wind speed from one turbine to another. So you don't need to just predict the wind speed in some general area over the wind farm. To do this right, you need to be able to predict the wind, ideally, at each turbine because of these high-resolution effects. This is an example of a model prediction for a ramp event in Colorado. This is the wind farm here. This is the Colorado border. We have strong winds coming down from the north, approaching the wind farm, and we see a spike over there that results from that. Louis talked about ensemble methods yesterday. That's affected our trend toward higher resolution because we're using our computing power, obviously, to run multiple versions of the model to get the statistical information in the ensemble, and that takes up computer cycles. So the rush to higher resolution hasn't been quite as rapid lately, but it's still there in both the ensemble world and the deterministic forecast world. And also we're going to see some new applications of large eddy simulations. Digress for a minute and talk about urban scale modeling. We've seen this before where we've actually resolved an urban complex in this example here. This is a 1 kilometer grid, so most decent sized cities will allow you to, 1 kilometer will allow us to resolve the metropolitan area. But the traditional way of representing these urban areas in all models has been to just modify the surface thermodynamic state and albedo and so on. So we get a different heat flux and moisture flux there to represent the urban effect. But we know in real cities there are buildings that stick up into the model atmosphere through a number of different layers. So there are new urban canopy parameterizations, they're called, to better represent urban effects in these high-resolution models. So here the red lines are model levels, and at each of the model levels that intersects a building, we get a direct insertion of heat in these multi-level canopy parameterizations, where before we just used to all put it in at the bottom down here and let it naturally move upward through the atmosphere with the turbulence. So this is a better approach to represent cities with higher resolution model. Getting down to really fine scales, large eddy simulations where you specifically represent the turbulence, that is explicitly rather than parameterize it. So here you see wind vectors in urban street canyons produced by an LES version of WRF. So in this case here, with this large eddy simulation version of WRF that actually represents buildings, you have a seamless modeling system that goes from the synoptic scale to the mesoscale down to the street canyon scale. So if you're going to track hazardous material that's released into the atmosphere in a city, you ought to have a model like this to do it. Really computationally demanding, but we're getting close to the point where that could run operationally. Where else might you need LES, large eddy simulation models with grid increments of 10 meters to 100 meters? Well, back to the wind energy industry again. If you're putting in a wind farm, you need to know details about the potential production of energy from each of the turbines, as we said. This is an example from this Cedar Creek wind farm. Each of the little colored dots there, they actually look like worms, but it's just a series of dots because of the way they line up the turbines. And each one of these little dots has a color, and that corresponds to the wind speed down here in meters per second. So this clicks off every 10 minutes, its colors change, so you can see waves of higher and slower wind speeds moving across that wind farm. And to diagnose how much wind you're going to get out of a potential farm before you put it in, when you have to decide whether it's going to be economically feasible, it would be useful to have a model with this resolution that could allow you to predict this kind of variability across the wind farm. This is what an LES version of WRF would look like. We have multiple domains like this, but instead of going down to 1 kilometer, we get down to about 100 kilometers. This is the terrain in northeastern Colorado for one of our applications, and this color coding here relates to the wind speed. So we see reds, high speeds moving in from the north. This is a ramp event about to impact a wind farm there and create a lot of additional energy. And this is one of the LES simulations over here to the right, again color-coded, and on the left we have the observed winds at the turbine nacelles. So this gives you an idea of how accurate this model rendering of the winds across the wind farm is. Again, this is about 10 or 15 kilometers across the farm. And, it's clearly not perfect, but it gets the general trend of the variability across there. So, we're encouraged. Moving on to specialized secondary models that are used often by commercial companies and the military and others. 20 years ago, we produced weather forecasts. We would give people the weather products, and they would do what they want with them. But now often people don't care about the specific weather variables. They have particular interests like ocean wave height, electrical generation capacity, and things like that. So we have these other special models attached to the weather model that produce new variables that are used by various stakeholders. So flooding is one of them. You have a flash flood model that takes the precipitation from the weather model, and these are run operationally. Wave height models, models that predict the spread of infectious disease based on meteorological input. Louis talked about meningitis in Africa yesterday. Sound propagation, electromagnetic wave propagation, wildfire probability and spread, dust storms, all kinds of aviation impact variables like turbulence, ceiling visibility, and so on are secondary products from the weather model that you have to calculate. Oil spill transport, that's a current issue, of course. Transport of hazardous material in the atmosphere, electric power consumption prediction, and so on. You know, there are dozens of other examples like this where people don't care about the weather directly. You need to input the weather into these special models, and it gives them the information they need directly without the human in the loop in many cases. Verification metrics for higher resolution. For models traditionally, when they've been coarser in resolution, we would use mean absolute error, root mean square error, and so on. But for reasons that I'll show in a second, that just doesn't do a good job with high-resolution models. Here we have wind speed here, and this is distance, so this is kind of a, well, it's not even a slice, but here we have a jet, high wind speed in this localized area, and say our model forecasts the jet here, this dashed line here. Gets the amplitude right, the position is offset, but there's still good information here. We know there's a jet in the area, and we'll watch out for it. But if you calculate the root mean square error, you're going to get penalized big time with this good amplitude forecast. On the other hand, say you have a really coarse resolution model, you know, it gives you this dotted line down the bottom. You're going to show up better with a root mean square error there than here. So we need something better to use with high resolution models. And one possibility is called feature-based or event-based forecasting. That is the front crossing the city at about the right time. We're not verifying the wind speed directly, but the front is a feature. This is a wind speed change here, and this is an event or an object that it's called. So we could compare the observed time of the event with what happens in the model, and that could be a forecast variable that would be more appropriate for high resolution. Now, lastly, let's wrap things up taking a look at quality assurance with high-resolution modeling, and you'll see what I mean by this in a minute. The general thesis is that it's easy to run a model, but it's not easy to run it properly. Now, what do we mean by quality assurance? You need to understand the weaknesses of the model, make the best choices about the model configuration. Most of these models, of course, just don't come out of the box and you stick it on the machine and turn the crank. You need to make choices about the parameterizations, the resolution, and so on. So we need to learn how to make the best choices, and we need to obviously thoroughly verify the forecast accuracy. We all know that, but a lot of our colleagues out there don't pay a lot of attention to this. And why is this a problem now? Well, let's look at the history. 25 years ago, virtually all modelers were at universities or in national weather services. They all had numerical weather prediction courses as part of their education. They all had atmospheric science backgrounds. 10 years ago, community models came on the scene like MM5 and WRF, and there was a rapid increase in the number of model users. Now, the increase in the number of modelers and models has continued to increase. Often, model users do not have an NWP course in their background, numerical weather prediction, so they don't have any formal idea of best practices for using a model. And sometimes the model users don't even have a good knowledge of atmospheric processes. In looking over the applicants for a workshop for a model that we want to put on next spring, half of the applicants did not have a formal background in numerical weather prediction. This workshop just teaches them where to push the buttons in the model to set it up. It doesn't teach them best practices, but half of them had never had a course in that, and 1/3 fully didn't know anything about atmospheric science. They were just going to pull the model out of the box and start using it with all the default settings. So why is this a particular problem now? Well, I've alluded to some of the issues. Easy access to turnkey community models. You get on the NCAR website and pull the WRF model off there, and you think you're a modeler. Online documentation and short courses, virtually for free, are right there. That's good, but, big downside that I'm talking about. Declining costs of computer hardware. We have more here than Pinhas and I did 25 years ago to play with MM1 or 2 or whatever. I'll be brief here on some of the corrective action to make this less of a problem, but take an NWP course. You shouldn't learn numerical weather prediction as on-the-job training. A lot of academic advisors at universities will tell the student to go off and read the technical document for a model, and you'll be a modeler next week. Again, learn atmospheric science. Remember that a good study of atmospheric processes should involve observations and theory. Don't just turn the crank on the model. You have a lot of observations out there that you can analyze and theory. So modelers just worry about the easy thing over there in the corner, at least easy in terms of turning the crank. They don't worry about analyzing observations or worry about what theory can tell them, where all three really need to work together. And lastly, don't underestimate the sensitivity of the model solution to the choices you make for parameterizing different physical processes. This is a lot of spaghetti, but this is time here, precipitation here. The red line is observed precipitation over a whole model domain for a case, and the dashed lines correspond to what the model gave you with different parameterizations for convection. So, many options there, and if you don't know which one is best for your case, you're going to have a problem. So, thank you.
Thank you very much. We have time for questions. Yiftach?
What do you mean by seamless simulation?
Yeah. You caught me. Seamless, well, we all know generally what the term seamless means. And, if it was really seamless, you wouldn't know the transition within the model as you went from synoptic scale down to LES scale. I meant seamless in that you could run them all together. They're the same dynamical core for all the resolutions. So you can run them together. They're obviously kind of stitched together between different scale ranges in some numerical context, but I meant that you could run them all simultaneously. It's not the situation you had 5 years ago where you would run a synoptic scale model first and then use that as input to the boundary conditions for the mesoscale model, run that, and use that as input to the LES model. This is all run simultaneously, but it's not really seamless as I implied, because as you go from the mesoscale model to the LES model, on the inflow boundary, you don't have any turbulence, and that's a big research problem right now. I guess people are trying to artificially generate turbulence on the inflow boundary to give you something realistic there, but no good way of doing that. So. Yeah. Pardon me? Yeah, when you say the different scale models do not agree, are you talking about an ensemble sense, like Louis says? Yeah. If you're talking about the different scales from synoptic to mesoscale to LES not agreeing with each other because they represent things differently, yeah. it's seamless in that you can run them all together, but it's not seamless in the sense that, when you go from, we look across those internal boundaries as in the nesting scheme. It's.
You have a question here, and then the one.
Yeah.
Colin.
Today, climate models are running interactive chemistry models. Is this work being done now at all? They have interactive chemistry to calculate real time?
There's a specialized WRF chem model that's run by, really developed by NOAA based on the NCAR WRF model. But yes, it's a specialized version of WRF that includes chemical processes that can be used for air quality issues and research and so on. So it's.
Veronica?
It was a remark to the question before, if the models are affiliating. Ensemble is of course one of the other, but what we also had yesterday to correlate different models with looking into the history of the last, let me say, 30 days. We have such a system developed which is called Meta Forecast, and this is something which really works. It's a poor man ensemble, but it works sometimes really very well. This is sometimes where you have the best, the least errors.
Is it similar to what Krishnamurti developed? Using different different models,
yes,
and to study where they are good and where they are bad.
It's only the Australians who are doing it. You're looking into the last 30 days and combining in an, of course, intelligent way these models. And the only problem is if one of these models was wrong and you have a very local effect, then this meta forecast is of course worse. But in all the other cases, it's a very good tool for the forecasters.
Steve, last, or yours?
I assume all examples you showed were one-way nesting?
No, typically we use two-way nesting. Yeah.
Yours?
You mentioned one application for forecasting for fires.
Yes.
I was wondering if you have widespread fires, can you actually also influence the weather so they can have some?
Yeah. There's a WRF fire model, and U-bound, does that allow the fire to feed back into WRF fire?
Currently, we have to walk more than that kind of fire online.
Yeah, okay, so there is fire dynamics that feeds back into it.
Okay.
I just wanted to add to your list of concerns. What we're finding with the user communities that are not modelers are they don't know how to initialize a model. And what I'm seeing in the university community is not only a decline in NWP, but almost a horrible absence of focus on initialization, and in some universities, data assimilation. And so when you get applications for these types of models, I mean, the sensitivities to the types of physics you bring to it are clear, and you're showing that. But how you initialize and how you assimilate these local data sets is probably could dwarf those differences.
Mm-hmm. Yeah, Penn State doesn't even teach NWP courses anymore, and that's where this model originated. So, kind of sad.
Thank you. Thanks very much.